Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 11 of stochastic hydrology. In the last class, we introduced the time series analysis. Especially we talked about what is a realization and what is an ensemble and what are time properties and ensemble properties and so on. Then we introduced the important concept of stationarity of time series. If you recall, the time series is supposed to be stationary if the properties across time remain the same. For example, the PDF of x t is the same as PDF of x t plus tau for all t. Then we say the time series is stationary. We also introduced the concept of weak stationarity. We reckon a time series to be weakly stationary of order f if all the moments up to order f are the same across across time t and t plus tau for all t. For example, weak stationarity of order 1 indicates that the mean, which is the first moment, is the same at time t and t plus tau for all t. Similarly, weak stationarity of order 2 indicates that both the mean and the covariance are the same at time t and t plus tau for all t. Then we introduce the autocovariance function and the autocorrelation and correlogram. Correlogram is also called as autocorrelation function. We plot rho k, which is the autocorrelation at lag k with k on the x axis. That plot is called as the correlogram, and correlogram, if you recall, indicates the memory of the process, that is how far into the past does the process remember. So, rho k indicates the dependence of x t on x t minus k or x t on x t plus k, depending on how we compute it. We today discuss an important aspect of stochastic hydrology, and we will introduce the concepts of data extension and forecasting. As I mentioned in the last class towards the end, in any hydrologic planning and design exercise, we rely on the observed data. So, the observations are made over a period of time. Say for example, you have 30 to 40 years of stream flow data at a particular location. Using these observed data, we want to make decisions on the designs that are going to serve us for the next so many years, next 50 years, 100 years and so on. So, the basis on which we make the hydrologic designs is the observed data sequence that we have. So, we have two different types of problems here, where in the first case we will be talking about decisions that have long term implications. For example, you want to build a reservoir, build a dam, and you want to fix the capacity of the reservoir or how high should be the dam. This decision you will make based on the historical data, let us say 50 years of past data, monthly stream flow data and evaporation data, rainfall data, etc. You have observed data for the last so many years, and based on that you would fix the height of the dam. This decision that you make based on the historical data has long term implication, because the dam will serve for next 100 years or so. So, this is a decision that you are making now which has long term implication. On the other hand, the problem of forecasting will have relatively short term implication. For example, you may have data for the last about 5 years and you are standing at the beginning of June of this year, and then you would like to forecast what is likely to be the monsoon flows in the reservoir, or what is likely to be the rainfall in the catchment area during this particular season, and so on. So, in the forecasting, essentially you are talking about short time durations, relatively short time durations, whereas in the extension and generation you will be talking about long time duration. Now, both of these rely on the observed data, and as I said, the main basis for both data extension as well as data forecasting is that the history provides a valuable clue to the future. So, we use the historical data, extract the information from the historical data, and then make an assessment of how the future is likely to be. So, in today's lecture, we will introduce both procedures for both data extension as well as data forecasting, and then in the subsequent lectures we will take this discussion forward. So, in data extension, as I just mentioned, we would be looking at the available data, let us say from 1970 to 2010 as an example. We have available stream flows for the last so many years, about 40 years, and we want to extend this record to let us say 2040, because we would like to make the decisions based on data from 1970 to 2040. So, this is the problem of extension of data. The data generation will include extension of data, procedures for extension of data, but additionally the data generation will provide us with several sequences of the data which has the same properties, same statistical properties of the observed data. By available data here, I mean these are the data that are observed, actually observed on the field. Then data forecasting, we will be dealing essentially with short time spans. Let us say you are interested in forecast for the next 10 days or forecast for the next 1 month and so on. So, we will be using the data up to the time period t. Let us say we are here, this may be June of a particular year. So, we have the observed data with us until that particular time. Then we would like to forecast standing at the end of June of a particular month, particular year, I am sorry. We would like to forecast what is likely to happen during the next time period, which is next month, July. So, this is the problem of data forecasting. So, data forecasting we provide as a function of the flows. In this particular case, we are talking about the inflow to a reservoir, inflow which has been observed during the month t, the previous month t minus 1, t minus 2 and so on. So, the entire history of this process up to this point is available with us. Using this entire history, we would like to forecast what is likely to happen to flow during time period t plus 1, what is the expected flow during the next time t plus 1, that is a forecast. So, we will today introduce methods of data forecasting as well as data extension. Now, in the absence of any method, let us say that we do not have any mathematical or statistical methods available with us, all we have is the observed data, and we would like to say this is the forecast for the next time period. What are the procedures that we may use? Intuitively, we may simply say that just take the average of this and put it as forecast for the next time period, or simply look at the what has happened during the last period and then say that the same thing is likely to continue for the next time period. So, like this intuitively we may do some forecasts based on the observed data. We will start with those kind of methods. But more formally, what we generally do is that any particular method that we want to use or any particular model that we would like to build for forecasting, we build it on first part of the data. We call that as calibration data. So, we build the model using the first part of this data. This can be either 50%, 70% or 80% of the available data, and then we calibrate the model and test the model so calibrated on the remaining part of the data. Let us say you built a forecasting model using this data, you calibrated that model and use that model for the next part of the data. Because you already have this data, you can then calculate the errors that you get by using the model. What I mean by that is that let us say you have used up to time period t, you have used the data for calibrating the model. Use the model so calibrated first to forecast the flow during time period t plus 1, if we are talking about flow forecasting model. So, we get a forecast, we denote it as f t plus 1, but we also have the observed data for time period t plus 1. So, the error will be x t plus 1 minus f t plus 1. It should have been actually x t plus 1, but we have forecasted f t plus 1. Similarly, at the end of time period t plus 1, you use the actual value of x t plus 1, not the forecasted value, use the actual value of x t plus 1 and then forecast it for x t plus 2. So, x t plus 2 is the actual value that has been realized, but f t plus 2 would have been your forecast. So, this gives you the errors in the forecast. So, we compute the errors as x t plus 1 minus f t plus 1, etc. So, you can now form a series of the errors themselves. Now, these are some of the basics of what we do in the forecasting problem. As I just mentioned, if we do not have any way of forecasting, any formal algorithm by which we can forecast, what we would have intuitively done is to simply take the averages. So, the first method of forecasting is simply based on the averages. So, let us look at what we do in this case. Let us say we have the data up to time period t. If we are talking about monthly flows and we have the data for last about 50 years, which means 600 values we have, and we want to forecast what is the likely flow for the next time period, that is 601st time period. Then the easiest way of doing it is take the long term mean, that is mean of all the values that you have observed, and put that mean to be the flow, mean flow to be the flow that is likely to happen during the next time period t plus 1. Then we proceed to next time period. So, t plus 1 you would have got the actual value that has occurred, take the values up to t plus 1 and forecast for t plus 2. So, use all the values that you have at your disposal, take the average of all those values and put that average as the forecast for the next time period. This is the first level of forecasting. So, this is the method based on simple averages. That is what is written more formally here. Whenever I use a cap here, it means that it is a forecast. So, x t plus 1 cap, which is the forecast for the time period t plus 1, also denoted as f t plus 1, this is simply equal to the sum of all the observed values divided by the number of time periods. So, t also indicates the number of time periods in this case, apart from indicating the specific time period here. So, you take all the values up to that particular time period, take the average of that and call that as the forecast itself. So, as you progress in time, you will have more and more number of values to compute the average, and that average you are putting it for as your forecast. As you can see, this method will not be useful where you have a strong periodicity or a trend etc. on the data. If you have a smooth process, let us say that you draw a smooth process. Let us say your time series is something like this. Then you are forecasting, let us say at this point, based on the values that we have got, maybe your forecast will be somewhere here, and next time forecast will be somewhere here. Like this it may keep on going. So, if you have a smooth process, this kind of average based procedures, this kind of average based procedure will work reasonably all right. Whereas, if you have a time series, let me show it here. If you have a time series which has performed like this, and then suddenly there is either a jump or a drop, then your methods will fail. For example, you may keep on getting forecast something like this, then the forecast will be slowly rising like this. So, you may not get a good forecast when you have either a jump or a periodicity or even a trend. So, if you have a trend in the time series something like this, then your forecast using the average methods will not work well. A improvement of the forecast using the average method is not to take all the values, but to take the last few values which have occurred, and then use the averages computed using the last few values and compute your forecast. This is called as moving average method. That means, we do not take all the values, but we keep a window of time fixed and take always the values within that window, and then compute your averages. So, first I will demonstrate what I mean by taking all the values and then computing the average and putting that as the forecast. Let us look at this value, this example, I am sorry. We have the data, these are the observed data 105, 115, 103 etcetera, like this. Observe here that there is a sudden drop in the data 120, it was operating around certain level, and suddenly there is a big drop here, and then there is a big jump again. So, this is the data. How do we use this data for forecasting? We have the observed data 105 and we want to forecast for the next time period. So, from these two data 105 and 115, you forecast 110. Then 105, 1110 and 103 you forecast 107.67. That means, you will take the average of all of these and then forecast 107.67. So, this forecast is actually for the next time period. Then you take all these averages and forecast 107.75. So, this has been got by taking the average of 105, 115, 103, 108. All of these values are used to forecast this. This forecast is for the next time period and so on. So, like this you get and keep getting the forecast for the next time period. So, the forecasts that are shown here are for actually the time period subsequent to that. For example, this is a forecast for this time period 103 and this is a forecast for this time period and so on. Now, as I said, instead of using all the values before, we use the values during a fixed time period and call that as the moving average methods. So, we keep shifting the time windows by one time step and then take the averages over the same number of time steps and call that as your forecast. What I mean by that is that let us say you have time period up to time period t. Use the time up to values up to time period t, take the average and call it as forecast t plus 1. In the next time period, you would have got one more value added to that. So, discard the previous value and then take the average over the same time periods t. Let us say t was 5 months and you are taking 5 months averages to forecast the next time period. So, when you move to the next time period, you discard the oldest value and keep the latest 5 months value to forecast the next value. When you go to the next time step, there are two time steps that you will discard. Take the latest 5 months value average and then forecast for the next time period and so on. So, essentially what we are doing is the window of the time over which the average is taken is kept constant, and this window is shifted every time by one time step, and the average is taken over the previous t time periods, and the average is taken as the forecast for the next time period. So, essentially we use the latest t time periods of known data, and this t remains constant, this window remains constant. Essentially that means that the number of points, data points that we use to compute the average remains the same across time as we progress on in time. So, let us see what we mean by that. So, we are talking about moving average of the order 3, which means essentially we are taking the average for using 3 values, 3 previous values. So, first 3 time periods 105, 115 and 103, we use this, take the average of that and then call that as forecast for the next time period 106.7. Similarly, when we go to the next time period, we discard this value and take the average of these 3 values 115, 103 and 108 and call it as the forecast for the next time period 108.67. Next time period, we discard these 2 values and take the next 3 values 103, 108, 120 and call that as forecast for this time period and so on. So, like this we get the forecast for all the time periods. So, essentially every time we are using 3 values, 3 previous values 105, 115, 103 which are the previous values to this and call it as forecast for that time period. So, this time window remains the same. Every time we are taking the previous 3 values and computing the average and calling it as the forecast. Now, we go one step ahead. That means, instead of reckoning the average only from the previous actual observed values, we reckon the average from the moving averages themselves. That means, now we will go one more order. We take the averages of the moving averages themselves and then compute the forecast. What I mean by that? We have the moving averages of order 3. Now, I will use 3 of these moving averages and compute the average of the moving averages and call that as the forecast. So, this is a smoothing process. So, we are smoothing. So, like this we use these 3 moving averages and get the forecast for this. Why do I write the forecast here? Because these 3 moving averages have used values up to this point, up to 120, and this will be the forecast for what has been recorded as 97. So, we would have forecasted 108.89 using these 3 moving averages. Like this, next time we use these 3 moving averages to compute the forecast for this and so on. So, we calculate like this and get the forecast. So, this is moving average of 3 by 3, second order moving average. So, these are some of the methods based on averages. One is simply take all the historical data, take the average, and average as computed thus would be taken as the forecast for the next time period. Next level, we take the moving average of the first order, where we fix the time window, always take the data for those those number of time periods, take the average and then put it as the forecast for the next time period. Then we, as I demonstrated here, we go to 2 orders of moving averages. We take the averages of the moving average themselves. For example, we take 3 moving averages, take the average and call it as a forecast and so on. So, these are methods based on averages of data forecasting. As I said, these methods will work well when the process is fairly smooth. You do not have very prominent periodicities, prominent trends, increasing trends or prominent jumps in the data and so on. So, when you have a reasonably smooth process, the methods based on averages work reasonably well. If you have data on monthly stream flows, for example, this kind of methods may not work well, because monthly stream flows exhibit a significant periodicity, especially in monsoon climates like ours, where June month flow is serially correlated with May month flow or the June month of the previous year and so on. So, there may be significant periodicities in the data. When you have significant periodicities or any significant deterministic components other than the mean, then these methods will not work well. So, we will now look at data generation. First, we will consider uncorrelated data, that is what we discussed earlier as purely random stochastic process or purely stochastic processes. If you see the correlogram for a purely stochastic process, the correlogram should indicate that the data are uncorrelated. If you have data which are uncorrelated, which means let us say you plot the correlogram rho k versus k, and all the correlations that you are seeing for k not equal to 0, they are all insignificant, they are all statistically insignificant, then the data is uncorrelated. Then what do we do? If the correlogram indicates that rho k is equal to 0 for all k not equal to 0, what I have shown here is the sample correlations, sample autocorrelations. So, they will not be exactly equal to 0, but they will be statistically insignificant. So, if you notice from the correlogram that for all k not equal to 0, the rho k's are all insignificant, statistically insignificant, then you can say that the data is uncorrelated, in which case if your distribution for x t is known, let us say that x t follows a normal distribution or a log normal distribution or gamma distribution, etc. So, if your distribution for x t is known or can be estimated from the observed data of x t along with its parameters, then what do? We have seen the methods of data generation earlier using the specified distributions. If you recall what we do there, we set R u, which is the uniformly distributed random number in the interval 0 and 1, to be equal to f of x, where f of x is the, if I can write it here, the capital F of x, or let us say if you recall we set f of y is equal to R u and then solve for y. So, this is what we do there, solve for y. F of y as indicated here is the distribution of the particular is the CDF of that particular distribution. For example, exponential distribution if you have, then you compute f of y and set it equal to R u, where R u is a random number, uniformly distributed random number in the interval 0 and 1, and then solve for y. And in cases where you cannot explicitly solve for y, there are methods available. For example, in the normal distribution we take the standard normal distribution and then you go to the tables which provide you the standard normal deviates, and then using that you estimate the y, you generate the values of y. So, this is what we do when you are sure that the data that you have observed are all correlated, that means are all uncorrelated, that means x t and x t minus 1 or x t minus k, x t and x t minus k can be assumed to be independent. Then you use the distribution for x t, generate x t, distribution for x t plus k, generate x t plus k, and so on. So, each time period you generate different sets of values, knowing the distributions of those particular time of the variable of that particular time period. But in general, in hydrology, most of the data are serially correlated. as I just mentioned, if you are looking at the stream flow during a particular month, let us say stream flow during August, this is serially correlated with what has happened during the month of July. Not only what has happened during the month of July, but also on what has happened on June month, also on what has happened during August month of the previous year, what has happened during August month or July month of previous year, and so on. So, the data will be serially correlated. The value that you have realized during a particular month will be dependent on what has been the value during the previous month, what has been the value of the same month during the previous year, during 2 years before that, and so on. So, these are called as serially correlated. So, we will see first a method based on the lag 1 correlation, when we have a significant dependence on what has happened during the previous month. And we introduce the concept of a first order Markov process, where if you have a rho k which is exponentially decaying like this, that is rho k can be approximated as rho 1 to the power k, that is rho 1 is the lag 1 correlation to the power k, and rho k tends to 0 as k tends to infinity. So, for a theoretical first order Markov process, you will get a correlogram which has an exponentially decaying shape like this. So, because most of hydrologic time series are serially correlated, that is x t is correlated with x t minus tau, we use several methods which are based on data generation, which are based on serially correlated data. And the first one that we are introducing, which is very commonly used in hydrology, is that based on the first order Markov process. When you have this, what does this mean? This means that the first lag 1 correlation is much more significant compared to any other lag correlations. So, as you can see, rho 2 will be much smaller than rho 1, rho 3 will be much smaller than rho 1, and so on. So, in fact, any correlation at any lag can be obtained from the correlation of the lag 1 itself, following this notation. This also indicates that the memory of the process is short. So, you may have 1 time step memory, 2 time step memory, and so on. That means, if you have x t plus 1, x t plus 2, and so on, x t plus k depends on x t plus k minus 1, or x t depends on x t minus 1. If you have the process where the memory is only to the limited extent of the previous time period, then you can use the first order Markov process. More formally, it is defined as, we will anyway introduce the formal definition of Markov chains, etc. Later on, but more formally we denote a first order Markov chain as, if you have probability of x t given x t minus 1, x t minus 2, and so on up to x naught, which is the complete history of the process. If we can approximate this as probability of x t given x t minus 1, then we use the first order Markov chain or Markov process in this particular case. What does this mean? This means that the entire information of the history of the process given by x t minus 1, x t minus 2, etc. up to x naught is all contained in the previous information x t minus 1 itself. So, the conditional probability of x t given x t minus 1, x t minus 2, etc. x naught can be approximated by probability of x t given x t minus 1. Then this is called as the first order Markov chain. In general, in hydrology, we can approximate especially the large time processes, for example, monthly stream flows, seasonal stream flows, etc., by the first order Markov process. And we introduce the data generation models for the first order Markov processes as indicated here. So, essentially what we are looking at, let us say we are looking at the annual stream flows. As I said, if you look at large time steps, monthly time steps, annual time steps and so on, and you are able to disregard or neglect the periodicities inherent in the data. That means, if the periodicities are not very strong and you can afford to disregard the periodicities, then we introduce the stationary Markov process as follows: x t plus 1 is equal to mu, which is the mean of the process, plus rho 1, which is a correlation of x t and x t plus 1, which indicates the dependence of x t plus 1 on x t, into x t minus mu x is the stationary mean, plus a random component. That is all, very simple generating process. So, this x t plus 1, the value that you are generating using the data that is available with you, will depend on x t through rho 1. So, the dependence of x t plus 1 on x t is measured by rho 1, and mu x is the long term mean of the process, which remains constant. So, we are taking the process to be stationary in mean. So, when we use this and we introduce the random component with the mean of 0 and its own variance sigma e square. So, this random component has a mean of 0 and its own variance sigma e square, and we would like to generate using this model, generate those values which will have the same mean as mu x and the same variance as sigma x square. Because we would like to have the same mean, the epsilon must have the same mean of 0, as we will presently demonstrate. But to maintain the variance the same, the sigma e square must have a particular variance. We will just see what happens to that. So, this model essentially generates x t plus 1, that is the sequence x t, it generates using the previous value of x t and the dependence of the current value on the previous value given by rho 1. Now, as I said, the properties of epsilon t plus 1 in this case are important. Epsilon t plus 1 must have a mean of 0 and the variance of sigma e square. So, for this process x t plus 1 given by this to have the same mean as mu x, what does it have to satisfy? We will take the model expected value. So, expected value of x t plus 1, and this is the model mu x plus rho 1 x t minus mu x plus epsilon t plus 1. So, that is expected value of mu x rho 1 into expected value of x t minus expected value of mu x plus expected value of epsilon t plus 1. And as I mentioned, expected value of epsilon t plus 1 is 0. This is what we have used, epsilon has a mean of 0. So, this value becomes 0 and this becomes 0, because this is mu x minus mu x and this is mu x itself. So, expected value of x t plus 1 becomes mu x. So, the model as defined by this will have the same expected value as the long term mean mu x, which is stationary. Now, we also want to see what happens to the variance of x t plus 1. So, x t plus 1 as defined by this, let us look at the variance. So, variance is simply expected value of x square minus expected value of x the whole square. So, I will take expected value of x t plus 1 the whole square here minus expected value of x t plus 1 the square minus expected value of x t plus 1 the whole square. if we simplify this, this gives the simplification. We have used the fact that expected value of epsilon t plus 1 is 0, and we have used the fact that expected value of x t plus 1 is equal to mu x itself. So, when we simplify this, you get sigma x square is equal to rho 1 square sigma x square plus sigma e square. All of this simplification has been given here. That means, sigma e square can be written as sigma e square is equal to rho 1 square into 1 minus sigma x square. What does this indicate? This indicates that if you want to have the same sigma x square, the idea here is that you would like to generate the data using this model, and this model will have the same mean mu x as the historical data. And for this model or the generated values to have the same variance as the historical data sigma x square, your mean of your standard deviation or the variance of the epsilon t plus 1 must be given by rho 1 square 1 minus sigma x square. That is the idea there. So, you must use your random components with 0 mean and variance given by this. As you know, as you can see, rho 1 is given from the historical data, you can estimate the rho 1, and sigma x square is the stationary variance of the time series which is also known. Now, a specific case where if x follows normal distribution, that is your observed stream flow data, for example, stream flow data follows normal distribution with mean mu x and sigma x square, then epsilon should be also normally distributed with 0 mean and sigma e square as the variance. So, we now introduce, if u t has a normal distribution of 0 1, then u t into sigma e, that is u t into sigma e is given by sigma x into root of 1 minus e square, is normally distributed with 0 mean and sigma e square. So, this is what we want. So, we will introduce u t into sigma e or u t into sigma x root of 1 minus rho 1 square into the model. So, that we are ensuring that the random component will have a 0 mean and a variance of sigma e square. So, we write the model now as x t plus 1 is equal to mu x rho 1 into x t minus mu x is stationary, plus the epsilon t, we write it as u t plus 1 into sigma x root of 1 minus rho 1 square. Why do we write this? This we are writing to ensure that the sequence that we generate will have a normal distribution with 0 mean, that is this random term will have a 0 mean and a variance of sigma e square. That is why we are introducing this. What is this u t plus 1? It is a standard normal deviate or the standard normal number, random number, which I repeat, it is a random number which follows the standard normal distribution, which is 0 mean and unit variance. The model we thus write is called as the first order stationary Markov model. First order because we are generating x t plus 1 using the previous value x t only and not x t minus 1, x t minus 2 and so on. So, we are just using one previous value. So, it is a first order Markov model. It is stationary because we are using the same value of mu x and sigma x for all the values. So, it is stationary both in mean as well as standard deviation. The first order Markov model is very popular in the hydrologic data generation, especially when we are talking about annual stream flows. The first order Markov model is straight away used, and annual stream flows, as I mentioned, are very useful in making designs, hydrologic designs. For example, to fix the capacity of the reservoir, you would require annual stream flows, and you generate the data using this particular model and use those generated sequences to make decisions on reservoir capacity and so on. Now, how do we generate values using this? From the historical observed data, you would have estimated mu x by your x bar or x bar. Then you can also calculate rho 1, which is the lag 1 correlation coefficient. So, mu x is known, similarly sigma x is known and rho 1 is known. We start the process by assuming a value of x t. Let us say you want to generate x 2 to kick start the process, you want to generate x 2. So, first you assume x 1. Remember, once you calculate these parameters, these moments mu x, rho 1 and sigma x, you forget about the data. You have to deal only with these moments mu x and sigma x and rho 1. So, first you assume x 1 and typically it is assumed to be equal to mu x itself, the mean which is known. So, that this term becomes 0 and calculate, take the standard normal deviate from your tables or any spreadsheets that give this normal deviates straight away, or you can use your calculators to get uniformly distributed random numbers and then convert them into normally distributed random numbers, or you simply write a MATLAB code, very simple MATLAB codes, MATLAB function you use to generate standard normal deviates. So, every time, for example, x 2 you are starting, x 1 you have assumed to be equal to mu x. So, this term becomes 0, mu x is the long term mean and sigma x is known, rho 1 is known, and this standard normal deviate you pick it up from the table or any of the functions that are available. So, you get x 2. From x 2 you generate x 3. So, here it becomes x 2, the value that is just now generated, and every time you change x t as well as the standard normal deviate, all other terms remains the same, you generate the next value and so on. Because you started the process by assuming a certain value for x t, when you generate these numbers for a fairly long sequence, for a fairly long sequence of numbers are generated, discard the first few values to do away with the effect of the initial value that you assume and use the remaining number of values. Remember, there are two major assumptions here. One is that the process x t follows normal distribution with mean mu x and sigma x square, and that the process is stationary in mean as well as standard deviation. That means, as you change from x t to x t plus 1, it will have the same mean mu x and same standard deviation sigma x. Let us see, as I just mentioned, we generate a large set of values. Let us say, if you had a observed data of 30 to 40 years, you generate sequences of 100 years. One sequence of 100 years, another sequence of 100 years and so on. How do we generate different sequences? Always by changing the random deviates here. So, by changing the random deviates you generate those many sequences. So, generate large number of sequences, and every sequence you discard the first 50 to 100 values. Let us say 50 years of sequences of monthly 50 years of sequences you have generated, you can discard the first 5 values or first 10 values and so on. Or you have generated a large sequence of 150 years, 1000 years and so on, which are typically used for large scale simulations of water resources systems. Then you discard the first 50 years, 50 values, first 100 values and so on. So, that the effect of the first initial value that you have used to start the process, that effect dies down. Because you are using the normal distribution, it is likely and often it happens that you generate negative values, because your standard normal deviates that you are picking up will typically go from -3 to +3, and therefore, your values that you generate thus can be negative. And if you are looking at hydrologic variables, physical variables, for example, stream flow and rainfall and so on, these values cannot take negative values. So, essentially what we do is, when we come across a negative value generated by this model, retain the negative value as such for generating the next value. So, when you are generating the sequence, you retain the negative values as generated by this model, but when you are using them in the application, let us say the sequence has several negative values and this sequence you want to use it in the application for fixing the reservoir capacity and so on. So, when you are using this sequence with negative values in the application, just replace the negative values by zeros. We will have ample opportunities to demonstrate the applications of these kind of models in actual decision making subsequently. But right now, let us understand how to use this model to generate values. So, let us take just about 3 to 4 values and see how we can generate. So, look at this example, 29 years of annual stream flows is available and that data is shown here. So, this is annual stream flow data at a river for 29 years is available. This is year number. So, like this 29 years and this is the stream flow data. So, we want to generate values from this stream flow data. If this were uncorrelated, what we would have done? We would have simply fit a distribution and then use the methods for uncorrelated data as we have discussed in the earlier classes and generated values from this. But because this is correlated, that is there is a serial correlation associated with this particular data, we use the method that we just described. We will use the first order stationary Markov process and then generate the data. To do that, what are the first steps? First is to estimate the mean, standard deviation and lag 1 correlation for this. So, we will estimate that. So, mean is estimated as 1269, sigma x is 281 and the lag 1 correlation is got by the covariance of x t with x t plus 1 and the variance itself. So, lag 1 correlation is estimated by R 1 is equal to C 1 by C naught. Recall that rho k is gamma k by gamma naught, where gamma k is a covariance between x t and x t plus k and gamma naught is the variance itself. So, using this we estimate rho 1, actually the sample estimates are indicated by R 1. So, rho 1 in this case is a sample estimate which comes out to be 0.255. So, to use the Markov model, all you need is these 3 parameters, that is mu, standard deviation and the lag 1 correlation. Once you estimate this, you completely forget about the data. All the information content that is necessary for you to use the first order stationary Markov process is all available here. So, to start the generation process, we first assume x 1, the first value, to be equal to mean, which is actually 1269.33. Here it is written as 1269, but the actual value is 1269.33, or we will use this as 1269 itself. So, we will use it as 1269 and so x 2 is generated as mu x plus rho 1 into x 1 minus mu x plus u t plus 1, which is a standard normal deviate sigma x root of 1 minus rho 1 square. So, u t plus 1 is, we can write it as u 2 here. So, mu x is 1269, rho 1 is 0.255 and x 1 minus mu x is 1269 minus 1269, because we have assumed this, plus this is the standard normal deviate got from the tables minus 0.464 and this is sigma x, which is 281 root of 1 minus rho 1 square, rho 1 is 0.255. So, this comes out to be 1143. So, once you get x 2, you use x 2 to generate x 3. So, where does x 2 come? X 2 comes in this place. So, this place you use x 2, this is mu x again. So, x 2 minus mu x, and every time you change this number. So, every time you are changing this number as well as this number, all other things remain the same, all other terms remain the same. So, you get x 3 is equal to 1328. Then using x 3 you generate x 4 now. x 4, this number has changed and this number has changed, all other numbers remain the same. So, you get x 4. So, similarly x 5, you use x 4 to generate that. So, x 4 was here. So, this number changes, and you get x 5 and so on. So, like this you can generate thousands of values using the first order Markov process. So, essentially what we did in this lecture is, okay, I will just complete that. So, you generate large number of such values. Let us say you wanted to generate 1000-year values, 1000-year flows. Why do we require such large sequences? We need such large sequences to simulate the performance of the system. It does not mean that the system itself will exist for 1000 years. We want to see how the system behaves if you have a sequence of 1000 years of flows, how the system behaves. So, system performance we would like to estimate. So, we typically require large sequences of data, and the first method that we have introduced to generate large sequences of data when the data are serially correlated is the first order Markov process, and it is famously called in hydrologic literature as the Thomas Fearing model, after the people who have proposed this model, Thomas and Fearing, famous hydrologists. This was proposed in the 1960s. So, typically in hydrologic data generation, Thomas Fearing model or the first order stationary model is the most commonly used data generation method. The limitations of this model is that it assumes normal distribution, that is the first one, and it also assumes stationarity in mean and standard deviation. The values that you so generate using the first order Markov process should preserve the mean of the data, standard deviation of the data, and also the lag 1 correlation of the data. We will see through certain applications, large case studies, etc., how this is done. So, essentially in this lecture we have introduced the data forecasting methods and the data and one of the data generation methods. In the data forecasting methods, we have introduced the methods based on the averages. So, take the average of all the data available up to this point of time and then call it as a forecast. That is the first simple method, and then the moving average method, where you keep the window over which you take the average, that window you fix and then keep moving the window itself. So, that is called as moving average method, and in the moving average method you have higher order of moving averages. That means, you take first the first order moving average and then take the averages of the moving averages themselves to take the second to get the second order moving average, and so on. Now, these methods, as I mentioned in the class, will work well for fairly smooth processes. That means, those processes which do not have a sudden jumps in the data or do not have a significant periodicities, significant trend, increasing trend or decreasing trend, etc. When you have processes like that, these methods will work well. Then we introduce the method for data generation, the first order Markov process, and specifically we have talked about first order stationary Markov process. In the next lecture, we will continue this discussion by first introducing non-stationarity in the first order Markov model.